Okay, so thank you very much for inviting me to this conference, which I've been enjoying very much. Today I'm going to talk about a very different kind of beam messenger astrophysics from what we have heard so far in the previous talk also. So I will talk about the work that my group has done in the last 5 years or so towards building a gravitational wave map of the local group of galaxies in order to understand which informations we can extract from it and how on the structure of the local group. And ultimately combine this map with the optical map, especially from the Gaia mission, in a fully statistical framework. So the work has not finished yet. This goal has not been fully realized. It will take many more years, hopefully before Lisa starts. But what I'm showing here are what I think important first steps. So the work I'm going to present have been led by students of mine over the years. Of course, all started with Valeria Corol's PhD thesis, and then proceeds with Orly Cope bachelor thesis, and Martijn Wilhelm and Michael Keim master thesis with me. And I keep collaborating with Michael, even if it's a PhD at Yale. So you will hear more from him as well in future years. Okay, so the local group, what is it? So this is the magnificent, I believe, stellar map of the sky by Gaia DR3, the last data release that was last December. So what you see, this bright and dark plane of the galaxy, of the Milky Way. The dark regions are the dust absorbed regions. You can also see very clearly on the bottom right, the large and small Magellanic Clouds. And if you squint on the bottom left, you could also see the Andromeda Galaxy and its satellite, the Triangulum. Actually, as you know, all these galaxies can also be seen at naked eyes. For a more informative 3D map of the local group, we can see here the Milky Way, again, the Andromeda Galaxy. Let me see. Do you see my cursor here? My pointer?
Yes, yes, we do.
Okay, so here again, the Andromeda Galaxy, the Triangulum galaxies, this is the small and large Magellanic Cloud. And these are the biggest neighbors of the Milky Way, but there is a plethora of satellites that have been discovered during the past decades. So in this talk, I will focus on our efforts to reproduce the structure of the Milky Way, the Andromeda Galaxy, and large Magellanic Clouds. And I won't have time to go and talk about the smaller satellites. Okay, so, but what are the open questions in the field? So why do you want a robust and as precise as possible map of the local groups? For various reasons, in order to understand the origin, so how our local group in our galaxy formed. Also the nature of dark matter, and also for testing modified gravity theory. So both for galaxy formation and evolution, but also what we call near field cosmology. And the game here is to compare cosmological simulations of Milky Way-like galaxies with with the observations in terms of phase space of stars, but also star formation rates, age, metallicity. The more information you get, the more accurate and precise your constraints can be. And so this is the game that has been getting more and more fuel from the Gaia data releases. So I work on Gaia, but as you know, I also work a lot in gravitational wave astrophysics. So for me, it was natural to think about gravitational wave sources and what gravitational wave information can add to this game. Which sources I'm talking about? Binaries with white dwarfs. So the most numerous binaries with white dwarfs present today in the Milky Way are detached double white dwarfs. And we think, Lisa, we will see tens of thousands of them, while instead being optically dim, only perhaps a few hundreds will be collected by Gaia and LST. There are other kind of binary with white dwarfs, accreting binaries, white dwarfs with helium core, but I will not talk about those today. So I will just focus on detached double white dwarf binaries, which are the most common. Why do I think they are excellent tracers of the stellar populations in the local group? Because they are abundant. In fact, white dwarfs are the most common fate of all stars. More than 97% of all stars in the Milky Way will become white dwarfs. They are pervasive because you can find them everywhere in the local group. And also, we think they do not receive big kicks at birth, and therefore they are born, they reside where their parent stellar population were. So that we don't expect any displacement. So they are the tracers of the parent stellar population. Okay. So take this out. Okay. So what are the complementarity aspects of gravitational wave and optical messengers? So in particular, I will focus for this talk on the optical electromagnetic wavelengths. But of course, this work has to be expanded and will be expanded to other electromagnetic messengers. But focusing on optical and its comparison with gravitational waves, as you saw in the Gaia pictures, Gaia sky map, optical is easily absorbed, and Gaia is not optimal in crowded regions. And so, for instance, galactic centers are not the best place to observe individual stars with Gaia at all. On the other hand, gravitational waves has no such problems, doesn't suffer from absorption or from crowding issues. So it has the potential to observe where optical cannot. Also, we have excellent, there are many distance indicators in optical, but in the local universe, we have the problems that we don't have a unique one. So we have parallaxes, but they work only for close by sources. Then we have spectroscopic distance. So we have variable stars. And each of these methods has systematics. With gravitational waves, we can use a single distance estimator throughout the whole local universe, which is completely independent from optical observations. So this is extremely important also for calibrating optical distance indicators. And finally, gravitational waves and optical can trace different populations. With gravitational wave, we trace the low mass stars through the whole local groups, while, for instance, for galaxy as far as Andromeda, which is at the outskirts of the local group, so almost 800 kiloparsec away from us, you can really observe individually massive stars. And also for the LMC, most of the stars individually observed are massive. Okay. So let's start with the Milky Way, and then we will proceed looking up. So this is how the Milky Way in galactic coordinates, so the same ones that you've seen in the Gaia sky map, will appear in gravitational waves. As far as I know, so far, there have been two methods to characterize, for instance, the disk of the Milky Way using white dwarf. One is by exploiting the copious background in the LISA detector. And another is instead by exploiting detected result binaries. And this is what we have done, and I will talk about our work, in which, as you see, we will also do the next step of combining with optical data. Okay. So first of all, please look on the right, and you can see what I meant by gravitational wave going in places where optical cannot. So now you see the galaxy, but in galactocentric coordinates, so centered in the galactic center. And you see that, if you can see it, the white dots is the sun. And the pink, yellow are the distribution of detected double white dwarfs by LISA. Okay, and you see that we can actually see in the galactic center and through the galactic center on the other side of the galaxy. Of course, this is something that cannot be done in optical. We cannot observe the other side of the galaxy. And you can also see here, so this is the sun, and we can have like a 360 degrees picture of the whole galaxy. As a reference, I put here the binaries, only double white dwarf binaries that will be observed by Gaia and LSST. And so you see that the reach is, in terms of distance, at least is far inferior. Most of them are within a few kiloparsec. Okay, what I'm showing here is the localization and distance error that we calculated with Fisher information matrix, and that we used together with the density distribution to make like mock simulated LISA data, which are the pink ones that you see on the left. So this will be the disk profile, and this is the, for instance, the bulge profile, and its fit. Assuming that we more or less know the model, we can reproduce the disk and bulge scales within a few percent. And particularly for the bulge, this is impressive, and we can do this exactly because we have lots of sources in the bulge that we can clearly see. When we assume that we do not know the model, and we try to fit for the wrong model, we show that we can actually distinguish, what is that? Is the 6?
No, this was not me, sorry.
Okay.
I don't know who did this.
We can distinguish between the different models because we have sources also in the outskirts of the galaxy. Okay. And then, so we made a joint fit between the shape that you can obtain in gravitational waves and the motion that you can instead obtain from optical data, the proper motion in particular. And for now, for this particular paper, we focused only on proper motion of double white dwarf. Someone likes to write on my slides.
Yeah, can you stop writing on the slide? I think it's Charles Marchetti. So please, can you just undo what you've written down?
And what we find out is that we can actually constrain the mass of the bulge, 17% level with no bias. Instead, we clearly see that we do not do great in constraining the mass of the disk, but this is quite natural because, as you see, all our optical data are very close to the sun. Very close to the sun. And so there is then a degeneracy with the mass of the halo. The next step in this work will be to use different optical tracers, like for instance, or Lyri, that go out to tens of kiloparsecs. So will give us a greater leverage. But this is was a proof of principle of how you can simultaneously join fit gravitational wave and optical data. Okay, what we did in that paper and what was to fit a smooth potential, an analytical smooth potentials. But the galaxy, as we know from Gaia, is messier than that. So the next question that we ask ourselves is how good are gravitational waves actually in tracing details, dynamical details of the Milky Way. In particular, since we have a lot of data in the bulge and in the galactic center, unlike optical data, we concentrated on the ability of gravitational waves to trace the central bar and also the spiral arms of the galaxy. And as a template galaxy, we used a simulation from Elena. Okay, so we populated the simulation with double white dwarfs, and this is it's the density distribution of resolved sources. Now, and you see that you can see the bar by eye. And this is extraordinary. You cannot do this in optical. In optical, you determine the properties of the bar just looking at dynamical effects on stars in the solar neighborhood. And here we are showing that in gravitational wave, you can actually see the bar by eye. The spiral arms, I should do this guy here, are clearly less well marked. These are the spiral arms. Okay, in the simulation, this is in density. So the density, this is because they are not very massive. So the constant in contrast in density between the spiral arms and the background is not great. Okay. So, but we wanted to put this in quantitative terms. So we Fourier transformed the density distribution. And in particular, what I'm showing here is only the amplitude of the m equal 2 mode. So a twofold symmetry in the density profile. And here is the, you see that there is the amplitude as a function of the distance from the galactic center. We have an increase in the amplitude and in decrease that span about 4 kiloparsec. And this is the bar, the signature of the bar. It gets contribution both from the disk and from the bulge, while here are the spiral arms. You see that you can see the spiral arms in the underlying meta distribution, this blue line. The black line, the black dots with error bars are the simulated LISA errors. And so already by eye, you can see that the bar can be detected, while in the spiral arm region, things get noisier. In particular, we showed, now please look on the right, that so this rising part, which is zoom in here, is excellent to constrain the axis ratio of the bar that we can get within very well consistent within 1 sigma from the bar axis ratio that you can derive from the stellar distribution. So very much consistent. And I repeat, the total density profile is not something that can be currently measured. Then from the phase of the m=2 mode, we can derive the length of the bar and the viewing angle under which we see the bar. So this is the phase, again, as a function of distance from the center. You see that there is a first part of constant phase. So this is the bar. So this that remain at a constant angle with respect to us. While here you see the wrapping of the spiral arms. So from this plot, basically we can infer the length of the bar and the viewing angle from the magnitude. So, so this is basically the results. So this is this contour plot of stellar density. We can, this is the viewing angle. The black line is the true viewing angle. We can recover the viewing angle within 1 degree. Then if you look at the red bar on top, this is our estimated bar length. That you see even by eyes that will reproduce the actual ones. And from the bar length and the axis ratio, we can recover the height of the bar. Again, excellent agreement with the actual one. Okay, so the next step here is to combine this data with the information that you can receive, you can obtain from optical. So this will be the next step. But now we look up out of the galaxies on the neighboring galaxies of the Milky Way. Okay, so here what I'm showing is a plot with 5 minutes. Okay, with chirp mass and orbital period. And the color-coded over merger time. Okay, so this line here, so at the interior, at the left of this line, there is a signal to noise ratio greater than 7 at the distance, for instance, for M31 Andromeda. This region is the region where we can detect binary. For the Small Magellanic Cloud, all this region is where we can detect binary. So this plot shows that there is always a parameter space, detectable parameter space, out to Andromeda. And here for reference, I'm plotted the verification binaries, and this is the Milky Way. So the Milky Way can detect a double white dwarf with very different chirp mass and period out to 60 minutes or so. What about Andromeda? Okay, so this is the population of double white dwarfs that we predict for Andromeda. We get that for years observations of LISA, we could get 12 double white dwarf and 60 for 10-year observations. Okay. The first remarkable thing is that we can observe at all a population of double white dwarf such far away. But the other remarkable thing is that these are all super Chandrasekhar systems. In fact, the other main point of this paper is that gravitational wave may be the only mean that we have actually to observe super Chandrasekhar systems, because the system being very massive means that are very small for the white dwarf equation of state, and so are very, very difficult to observe in optical. In fact, we have no confirmed candidates observed so far in the galaxy. And with this paper, we made the point that you can only observe them copiously in the galaxy, but even out to the Andromeda. And this is very important to pin down the progenitor of supernova 1A. Okay, and the last part of my talk, last few slides, is on an ongoing project, which I'm very excited about the Large Magellanic Cloud that you can see here from the Gaia DR3 release. Okay, so what we did here is to take the several models for the Large Magellanic Clouds and understand what we can say with the gravitational wave data. For instance, we assume three different star formation history. Look at, for instance, the blue one. The star formation history is likely increasing with time, always consistent with data. By contrast, we explore another star formation history in which there is a burst 10 gigayears ago, and then the star formation is constant at the lower level. Can we distinguish between these two with gravitational waves? So what we have shown is that these two star formation history give a different number of detections by a factor of 2, in particular different in massive systems, because the star formation history in which you have a burst in the past means that massive and short period binaries will mostly have merged by the time we observe. So today, in fact, I don't have the plot to show you, but we show in this paper that you can analyze the mass and period distribution and see that they are systematically different. So we think that from the property of the observed binaries, given all the other elements equal, you can infer the star formation history. We also show that the number of binaries scale basically linearly with the still unknown stellar mass of the galaxy. So this is another indicator of the mass of the galaxy. What is the next step? So all these detected binaries are very, very bright. In fact, are extremely well localized. Like 50% of the binaries has a localization less than in the Large Magellanic Cloud, less than 2⁻⁻² square degrees. And this allows to make a very nice map in gravitational waves. So what you see here is the Gaia map and overplotted the Lisa density contour. So the next step is to compare these density contours with the optical density contours and the also dust map to have the most complete and accurate picture of the LMC and also of the bar. So derive the morphology. The idea is that with gravitational wave, you can go in places like here, that you think you don't have stars. Okay, so this is all I wanted to present today. Thank you for your attention.
Thank you. Thank you very much for the presentation. So now it's time for maybe a couple of questions. Don't be shy, raise your hands. Okay, Raphael.
Hi, Elena, thank you for your talk. I was wondering if you had thought about using the white dwarf to detect in Andromeda and Large Magellanic Cloud to recalibrate the cosmic distance ladder and use it for cosmology, for example.
Yeah, so that's an excellent point, and I think a very fruitful line of research. Yes, I would like to do that. And go into the dirty detail of calibrating the various different methods using the distance from gravitational wave. Yes, this is a very good point.
And if I may ask a second question.
Yeah, sure.
So with this method, you're able to trace the positions of white dwarfs. Do you know to what extent tracing this population of stars is equivalent to tracing other populations of stars, or are they distributed the same way in the bulge and in the disk as the other, let's say, ordinary main sequence stars?
Yeah, so the white dwarf that we observe in LISA mainly trace stars that were born within a few giga-years, mainly from us. So not in extremely old populations, mainly. So this is something that needs to be taken into account when compared with the optical information. Second point, now we think they are not displaced with respect to the underlying parent population because during their formation and evolution, they don't receive substantial kicks. So under this assumption, we have proved that there is no bias in spatial displacement.
Thank you.
Okay, I see no other hand raised. So thank you, Elena Rossi, again. And we move to our next speaker.